All right, so good afternoon, everybody. Here we are in Statics ES 2110, and the date is September 4th. This is not a regular meeting. We usually just meet on Mondays, but we're meeting on a Wednesday because we did not meet Monday because of Labor Day. So I just want to make sure everybody's up to speed and answer any questions and sort of proceed forward in our material. I wanted to let you know I've graded your unit conversion problems and everybody did very well. Your format is good, your work is good, everything was complete. I wanted to show you, I'm going to switch roles to student just so that you'll see kind of more what you see when you get into your Moodle page. But every time I grade an assignment, I have the opportunity to leave comments. And this time there was nothing really meaningful that I left, just that you all had good form, everything looked really good. But when you look at your homework submissions, do take a look at the comments, because if there's something, sometimes I'll put something there that will help you in the future, or will give you an opportunity to correct something that is not correct, or just turn in a better homework assignment for a better grade the next time. Although, like I said, that is not applicable in this case because everybody did a good job. Right. So if we take a look at our schedule, we can see that here on September 4th, that's our 6th class period. And we are working our way through for the chapter 2 homework. So the chapter 2 homework is actually due on September 13th, which is a week from today. So we are just proceeding through the material. The other thing I wanted to show you, I hope you're all familiar with this, but you never know, is that I do have the textbook for chapter 2, part 1. I was working with Oz and Joey yesterday on dynamics, not on statics, but if you have a different version of the textbook, your problems may not be exactly the same, but it's fine. As long as you don't cherry pick, like you don't want to go to chapter 11 for problems 1, 3, and 7, and then go to, edition 12 for the other problems. As long as you do them all from the same edition, you'll get the body of material that you need to be successful on the quizzes and on the midterm, and also on the final exam. So, working from this, when we take, that says chapter 2. Oh, I know why that is. Okay. So what we're doing here is we're doing the addition of forces. And the first thing I would like to point out is, let's do this. I'm gonna give you some more material here. Stop sharing. There we go. And I'll start writing here. When we add, or I want to get, hang on. There we go. Forces are vectors, which means that they have both magnitude and direction. So for this class, the governing equation that comes up over and over again, and that can be applied in more ways than a human could possibly imagine, is that vector force is equal to scalar mass times vector acceleration. Now, implicit in this equation is you may have more than one force, so there may be a summation sign here. And also implicit is force and acceleration are both vectors, and that means that they have to occur in the same direction. So the implication of that is, if you have an object, and if I'm not going to drop it, I promise, it's kind of fun, but I won't do it. And if I drop it, the force will be directed downward, because gravity, which is the acceleration, is directed downward. If I were to push this chair in this direction, only the part of the force that is horizontal will actually move the chair. I can push on the chair downward all I want, and unless I'm able to break the floor, the chair is not going to go anywhere. If I push at it with an angle, only the part of my push or the force that goes in the direction of the motion actually causes the motion. So, and this ties into some really interesting ideas later on. It also implies that in order for something to sit still or to not accelerate, so in other words, if the acceleration is equal to 0, you get a statement that says the summation of forces in any vector direction is also equal to 0. That means in order for a structure to stay still, that means that all the forces in all of the directions have to be equal to 0. And if not, it's going to move. Forces cause linear translation motion. Later on, we'll talk about moments or torques, and they cause rotations. But it is a true statement that the summation of forces in any direction have to be equal to 0 in order for an object to not accelerate, and specifically here to sit still. All right, so that means it becomes really important for us to be able to add forces. Because if you can't add forces, how do you know if they ever come out to be 0? That would be quite a trick. Now, in your textbook, now, first of all, and you can be honest with me, how many of you have started the homework for chapter 2 yet? Okay, good, because I'm going to tell you to not do certain things. All right. They talk about 2 different kinds, or they talk about 3 different ways to add. How can you add vectors? Specifically forces. Okay, and they give you a couple of different methods to do that. One is called the parallelogram law. Another one is called the triangle law. And the third one is vector math. Okay, so the reason that I put these on my paper and I want to talk about them is I do not want you to use the parallelogram law, and I do not want you to use the triangle law. I want you to start off using vector math. The reason for that is everything that we talk about at the beginning, and this is a great attack method for solving problems in both statics and dynamics. We start working in 2 dimensions, and then we expand our discussion into 3 dimensions, okay? The parallelogram law and the triangle law will get you nowhere when we start talking about 3 dimensions. So the only thing that will work and will continue to work is vector math. So if you just add and subtract 2-dimensional vectors, adding and subtracting 3-dimensional vectors is an easy corollary. Maybe easy is too strong, but it's directly built on vector math. So I like to just start out using vector math from the beginning. And I've never seen a case where you would be better served to use the parallelogram law or triangle law, especially when you start working with 3-dimensional stuff. All right, so how does that work? My screen just blurred on me a little bit. There we go, that's better. Okay, so how? Well, the first thing is we have to assign or decide on directions to use. And initially, we like to start out with X and Y coordinates, where X is horizontal and Y is vertical. And that means that there is a 90-degree angle in between them. Now, just for reference and fun, you don't always have to do this. There are other ways that sometimes are more suitable. For example, if you have a block sliding down an inclined plane, if you have a rope pulling it this way and some friction pulling it this way, and the weight pulling it this way, which resolves into 2 forces and into some force of the plane pushing back on the package, it's often better to orient your coordinate system along and perpendicular to the inclined plane itself. But for now, we're going to start out this way. And it works well for a lot of, there's other ways to do it as well. You can do it, like if you have a car going around a circle track, or if you're, let's just say, if you have, like, they call it the Greek waiter trick, where you have a string and you have some object attached to it. You have one type of motion going this way, and you have another force acting this way that balances a force acting in a different way. And you can often just rotate that coordinate set as you go down into a normal and a tangential direction, which mathematically becomes much easier if something's moving in a circle or in an oval or something like that. So there's other types of coordinate systems. But the thing that you may notice is that except in rare instances, all or almost all utilize perpendicular axes. So in other words, it would be quite unusual to use axes where you had X and, 40 degrees off of X. The reason for that is, if you remember the theorem of Pythagoras, if you have things that are perpendicular to each other, x squared plus y squared equals the hypotenuse squared. Whereas if they are not perpendicular, if this angle is not equal to 90 degrees, gotta scoot that up, then instead of using theorem of Pythagoras, you have to use the law of cosines. And so the math just gets more complicated to find those numbers. So you simplify the math right off the bat by using perpendicular coordinate systems, whatever they happen to be. All right, so what does that mean for us? Well, let's say, for example, if you have this is looking down, so this is a plan view. I have a boat and it's being towed by 2 ropes. Okay, if the boat moves in this direction, but does not move in this direction, I can guarantee that the summation of forces in this direction, which I would call y, it's not vertical, but it's across, would be equal to 0, or else the boat will drift. If the boat is moving in this direction, you can guarantee that the summation of forces in that direction is not equal to 0, that it would in fact be some positive number, because otherwise it's not going to accelerate. Okay, and I'm not talking about motion directly, just acceleration specifically in that case. But so today and in chapter 2, it is very important to use vector math to add vectors as a foundation of static analysis. So that's where we're going with this. But in the meantime, we're just going to take a look at adding some vectors. And that's kind of what the first part of the homework is going to be about. All right, so if we take a look at the textbook, all of this just talks about some different ideas about adding vectors. And the first one states some properties. So I think I might have mentioned this, but your textbook authors indicate vectors by bolding a symbol. So for example, bold P means the vector P. Bold Q means the vector Q. I can't do that. It's very difficult for me as I'm writing notes really quickly to bold letters. So I just use this instead. Or occasionally there's another symbol that you can use like this, but those all mean the same thing in my shorthand. So going back and taking a look, this, first of all, vector P plus vector Q equals vector Q versus vector P. That's just the commutative property. So vectors do obey the commutative property of addition. Similarly, if you have three vectors that we are adding together, you can group them together in different configurations. So if you have three vectors, P plus Q plus S, you can group together P and Q and add them together first and then add S. Or you group, for example, Q and S together and add P. That would be the associative property. So vectors also follow the associative property of addition. All right, so we come up with this idea then, which is called the resultant. And the resultant means a vector that has the same, and I will put this up, magnitude and direction as the sum of two or more vectors. Okay. So in other words, you could write that as being vector P plus vector Q equals vector R, and vector R is the resultant of P and Q. Okay, so kind of the inverse of resultant is a component, which is the, I'll put this in air quote, piece of a vector in a particular direction. So in other words, vector R could be thought of as some component Rx in the X direction. And I'm trying to think about, I think you do this in math. I'll show you a different notation in just a minute. And R sub Y, this would be the X component of R, and this would be the Y component of R. So in another notation, this is called unit vector notation, which we'll talk about. It means a lot more than this. But for now, we can just call it R vector equals the value of R sub X in the X direction, which we designate with the unit vector I, and R sub Y in the J direction, which is the unit vector in the J direction. Now that means a whole lot more. We're going to talk a lot more about what I and J are, but for now we can think of it, part of what its meaning is just being this notation to distinguish how far it goes in the X direction and how far it goes in the Y direction. Okay. All right, so going back to our textbook then, we can talk about getting the resultant, adding up. Resolution of force into components means breaking it up. Okay, so resultant adding components, breaking up into directions. And then we get some sample problems where we actually do this. Now, you'll see here, they're using the parallelogram law, which I really, like I said, I do not want to do. So I'm going to start off by showing you how to do sample problem 2.1 without using the parallelogram law, with using some vector analysis. And then we will continue on with our work. All right, so what we have here, and I'll draw out the picture, and then we'll, I'll go ahead and make it big after we go through the whole problem. We have two vectors, P and Q, that are pulling on a nail head, okay? And we're told that vector Q has a magnitude of 60 newtons. And if you take a look at the trig, you'll see that it's 25 plus 20, or 45 degrees from the horizontal. We then have vector P, which has a magnitude of 40 newtons that acts 20 degrees from the horizontal. And what we are asked to find what is the resultant. And the resultant means P plus Q. Okay, so the first thing we do is, and this would be a free body diagram. This would be an appropriate free body diagram. If you don't want to draw the nail in a sketch, you can just put a point there, because once again, it's just the minimum amount of information that you can convey. But what we can do is we can take vector Q and break it into some Q sub X in the I direction, added to some Q sub Y in the J direction, or along the X axis and along the Y axis. And I and J are very, very commonly used. It's unusual that you would use other notations for that. So just so you know. All right, then we could break up P into its components, which we would just call P sub X in the I direction and P sub Y in the J direction. All right. Now, how do we do that? Well, if you take a look, let's just take a look at Q. We know that it has a magnitude of 60 newtons, and we know that it acts a total of 45 degrees from the horizontal axis. If I set my axes like this, X is horizontal and Y is vertical, that means that I can think about vector Q as being some piece Q sub X and some piece Q sub Y. And that those will be the components. All right, well, if you look at this, also if I add them together, because this is a right angle, that will be a complete expression. So Q sub X squared plus Q sub Y squared will equal 60 newtons squared. All right, well, if I look at that as being a right triangle, I can just use a little right triangle trig, and I can say Q sub X then must be equal to 60 newtons times the cosine of 45 degrees. And Q sub Y has to be 60 newtons times the sine of 45 degrees. Because as you remember, sine is opposite over hypotenuse. Opposite over hypotenuse. And cosine is adjacent over hypotenuse. All right. Similarly, if I look at vector P, I see that P is 20 degrees off of that x-axis, and its magnitude is 40 newtons. So doing the same thing, I can say P sub X is 40 newtons times the cosine of 20 degrees. P sub Y is 40 newtons times the sine of 20 degrees. Now, if you recall, sines and cosines are dimensionless. In other words, they're just a number. So you multiply anything, a dimensionless number, by newtons, your answer is going to be in newtons. Now, at this point, I would like to caution you to make sure that your calculator is in degrees. Your calculator may default to radians, or called a grad. And those are two different units that will give you different values if you punch in 20. So in other words, if you have a circle and you go around the circle is 360 degrees. It's 400 grads, and it's 2 pi radians. So these are all the same amounts. You can use those as conversion factors, but if you plug it into a trig function, you just want to make sure that your calculator is set to degrees, because otherwise you get a weird number. And sometimes you can check it. You can do the, like, for example, you can check a sine or a cosine of 90 degrees, and if it's 0 and 1, then you're fine, right? But if it turns out to be 0.642, then you know you're in some weird set of units. Okay, so if we go ahead and do the math, I don't even know if I didn't bring my calculator, so I got to see if my phone will do sines and cosines. It says it will. So let's take the sine of 45, let's see what that number turns out to be, 0.707 square root of 2/2, right? So that's good, times 60. So if I take 60 newtons times the sine of 45, I get that the value of Q sub y is 42.4 newtons. Similarly, for Q sub x, I'll put this here so you can see it. I'll do the cosine of 45 degrees, 0.707, which is also the square root of 2, which makes sense. Because 40, and then multiply that by 60, and I get the same value, Q sub x is equal to 42.4 newtons. All right, how about P? Well, if I take the cosine of 20 degrees, and I multiply that by 40 newtons. Oh, not 440. No. I get 37.6 newtons. And P sub y, the sine of 20 times 40 newtons, that gives me 13.7 newtons. Okay. All right. Now, before I add those, there's a couple of other things that I want to point out. X is generally taken as positive to the right. Y is generally taken as positive going up. So if I look at both of these vectors, P goes over to the right and up, so it's positive and positive. Q goes over to the right and up, so it's also positive and positive. If we had a different vector, PQR, let's say S, and we attached to that nail head, and S was like this. Okay, this is negative in the X direction, but it goes up, so it's positive in the Y direction. If you had it attached like this, yeah, this is vector QRST, for example, it goes over to the right, so that's positive in the X direction, but it also goes down, so it's negative in the Y direction. So at that point, before you add, you have to make a decision as to whether they're both positive or one's positive, negative, or and so forth. All right, so I can set up my two vectors. I can say Q then is equal to Q sub x, which is positive 42.4 newtons. I'm giving it that little I as a notation, plus 42.4 newtons J. And then my P vector is in the X direction, 37.6 newtons I, and 13.7 newtons J. All right, now there's something that I would like to point out to you. Because of the theorem of Pythagoras, if you take 42.4 squared and add it to 42.4 squared, you'll come up with 60 squared or 3,600. Similarly, if you take 37.6 squared plus 13.7 squared, you'll come up with 40 squared, which is 4 times 4 is 1,600. Okay, so that's because it's the theorem of Pythagoras. All right, so now how do I do the math? I add together the X components. So I add these two together. It's going to be 0.0, carry a 1, 7, 8, 9, 10, 4, 5, 6, 7, 8. 80 newtons in the I direction. And then over here, 7, 11, 6, 5, 56.1 newtons in the J direction. And that is the answer to this problem. Now, there are other ways to express this. And if you look at this problem, you'll see, for example, that they're doing a trig solution and they're doing a parallelogram solution, and they're reporting the answer as a magnitude at an angle, which I will do for you. Sometimes that comes in handy, but it's a different way of reporting a resultant. Okay, so what we'll do here is I'll write out my numbers again. The resultant is 80 newtons I plus 56.1 newtons J. All right. Come on, wake up. All right. So if I were to draw that, so in other words, what we're saying is attaching these two forces, P and Q, to this nail head at A is exactly the same. In other words, it will have exactly the same effect as if I attached a single force R, which I don't know the absolute magnitude and I don't know the direction based on an angle, but I do know that it's 80 newtons in the X direction and 56.1 newtons in the J direction. Okay, so if I want to report that as a magnitude, how do you think I would get the magnitude from these two numbers? Yes, theorem of Pythagoras. So the magnitude, here's the notation, the magnitude of R then is equal to the square root of 80 squared plus 56.1 squared. And what does that value turn out to be? Anyone? 97.71 newtons, okay? And then we can take that back and put it here. And we can say, what is this angle? Which I'm just calling generically theta. Well, I have three sides. I can figure out the angle using a trig function. If I want to go back to my original data, opposite, adjacent, that would be the tangent, right? So the tangent to the -1 of the opposite side over the adjacent side. And what do I get for an angle? How many? 35 degrees. Okay, so that means that another way to write this would be resultant R is equal to 97.7 newtons at an angle of 35 degrees from the horizontal. So this number and this vector and this vector are identical. This number is written in vector notation. This is written like a little Feynman diagram, but the information that they convey is exactly the same. Okay. Do you guys have any questions at this point? All right, well, good. So let me take a look at your homework to get started. Now, the other thing is when you look at the homework, you'll see it's kind of written in different steps. I think we've talked about this a little bit, but I'll go through it one more time. When you go down to the submit chapter 2 homework, when you open it up, there are different problem sets, okay? So right now, as I said, do problems 2.2, 2.6, and 2.9, use trigonometry and vector components, not the trig rule, but trigonometry like we just did. Don't use the parallelogram or the triangle rule, okay? So even though there's 3 problems here, 3 problems here, 2 problems here, 3, 2, and 3, okay? These taken all together as a single homework assignment that will be due on September 13th. So based on your work in this class, you probably would surmise that waiting and trying to do them like the day before would not be a great idea. So you want to kind of get started and do a few and then ask me questions when you have problems and go ahead like that, right? All right, so the other part is, once again, I think you probably already figured this out, but I'll show it to you anyway. When you look at the textbook, because the PDF file was so big, I couldn't get the whole chapter into a single PDF. If you're working from a textbook of your own, you're going to be fine. But if you go down here, the problems are scattered throughout the book. And generally speaking, there will be a page called Solving Problems on Your Own, which is sort of a summary of the section or sections of material that came before it. And then there will be some problems. So the first homework problems, which go through 2.9, are right here in this section. But if you go all the way down, you'll see that there's some more homework problems going up to problem 242. But to get to problem 243, you would have to go to the second part of that textbook. So textbook chapter 1 part, chapter 2 part 1, you'd have to go here, and then the continuation of the chapter would occur there. All right. All right, do you guys have any questions or comments? What's that? Okay, it's all dynamics. Okay, so yeah, so this chapter is like I said, what we're doing is we're learning the fundamentals of adding and subtracting vectors, finding resultants, finding components, because we're going to use that as we proceed to see if things are accelerating or not. And if they're not accelerating, we can use that as a condition, as a theory, summation forces of x in all directions equals 0, in order to determine maybe an unknown force or an unknown location of a tether, or something like that. So, all right. All right, well, I'll stop recording then. And that's all I have for you today, except for just let me know if you need help on your homework.